Okay, good morning all. Today we are going to discuss about the optimization algorithm for deep model learning. So there are nine various optimization algorithms are there, starting from stochastic gradient descent, followed by stochastic gradient descent with momentum as well as Nesterov momentum are the three techniques. And after that there are adaptive techniques are also there called AdaGrad, RMS props, RMS prop with Nesterov momentum, Adam, Newton's method as well as conjugate gradient method. Among this, what are these? This basic definition, everything we have discussed in the second unit. So now we are going to see how are we going to apply this basic formulae what we have seen in the second unit as a optimization technique for our deep model. Let us go one by one. The first algorithm what I am going to discuss you for deep learning model is stochastic gradient descent algorithm. And here what this algorithm is doing is it is doing formula finding for updating the gradient vector along with the direction of the parameter so that the cost function can be reduced. So that is the idea here. So let us see how this model is working. The algorithm name what I told is SGD update, and it requires a learning rate schedule for every iteration, which is nothing but equivalent to the eta parameter in our ML. So it is termed as eta 1, eta 2, etc. Until there are k iteration, it is going to have eta 1, eta 2 up to eta k. And what else it need is the initial parameter theta to be optimized for minimizing the cost function. So during the first iteration, what we are doing is while until the stopping criterion is met, in the sense that are we going to reach the lowest cost of the function. So that is the criterion for a deep learning model. So until the low cost of the optimization function or cost function is reached, we are going to update this algorithm. So what we do first, we are identifying a sample mini batch training set which contains m different data sample along with its corresponding target y1, y2 up to ym. So using that data set, we would have trained our deep learning model. And after the training, we may be able to calculate the loss function by comparing the actual output f of xi with the desired output y of I for the initialized theta parameter. And that loss function is being summed up together for all such m samples, and that is being taken into a gradient vector by taking the derivative of this loss function with respect to the parameter theta. Okay, so that is your gradient vector, and this gradient vector is going to be applied as a update function for the stochastic gradient descent. So what the stochastic gradient descent is doing, the error is being calculated for a mini batch size, then only the update is happening. That is the idea of SGD. It's very clearly shown in this algorithm. So at the end of iteration, the gradient calculated is being applied over the parameter theta to change its direction. So when the gradient is positive, the direction of your current parameter theta will be reduced. If it is negative, the current parameter direction will be improved with respect to the learning rate parameter. So that is the idea. Okay, so when I am considering the learning rate eta, which is going to be decayed over a certain period of time, suppose I say eta k is the learning rate over time at iteration k, let us assume. And so eta k can be written according to the decaying formula 1 minus alpha into eta naught plus alpha eta tau, where this tau is the finest time of iteration. So alpha can be rewritten as k by tau. That is, among the tau iteration, now we are at the kth iteration. So at every iteration, it is going to have a significant contribution of 1 by tau into your the ratio of your learning rate parameter. So now when k is 1, eta 1 is nothing but 1 minus alpha into eta naught plus alpha into eta tau. So that is the maximum value of that e tau is being taken. And here the assumption is e naught may be taken some lowest value, as well as the eta tau may also be given a ratio of your eta naught. Suppose I assume eta naught as 0.1, the eta tau may be 0.01 eta naught, so it may be around 0.001. So this is the way the starting learning rate value as well as the decaying rate of the learning rate is given, so that will reach up until the end, but the ending value is also being taken here as one of the hyperparameter. So this is the way the learning is happening here. So according to this, when k is tau, it's the highest value of your eta k, when your k value becoming the tau. So eta tau is equal to 1 minus alpha into eta naught plus k by alpha, right? So in place of k I am replacing now by tau. So tau by tau will be getting cancelled out. So it is becoming now 1 minus alpha eta naught plus eta tau. So accordingly, when I am applying this over my eta 1, it is nothing but 1 minus, the alpha is now becoming 1 minus tau, right? So thereby it is becoming 1 minus 1 by tau into eta naught plus 1 by tau is nothing but your alpha into eta tau. So that can be simplified as tau minus 1 into E naught plus eta tau by tau. So finally eta tau is going to become E naught plus E tau all the time. So this is the relation between your initial eta naught as well as your final eta tau. So at the final stage, automatically your eta k will be reaching the assumed value eta k. Sorry, eta tau at the beginning itself. Okay, so this is the way the learning rate is being updated in a stochastic gradient descent, and the same algorithm is going to be further slightly modified by introducing another parameter called the momentum parameter. So it is going to have yet another term for updating your parameter set vector. So along with the learning rate as well as your initial theta value, we are having here an extra momentum factor, as well as for the momentum factor there are two things already we know. It is being controlled by velocity as well as acceleration, right? So here we are considering the velocity of this momentum called v, and we are going further. While the stopping criterion of your SGD with the momentum is not yet reached, what we are doing is, again we are taking the mini batch data set and we are computing the gradient of your deep learning model as like the earlier one, and we are computing the velocity update also for the momentum factor by taking the derivative of your earlier velocity value with respect to the current gradient. So the gradient value, whatever it is, the rational learning rate parameter is being added, and along with that it is going to take the updated value for your velocity vector, and after computing this velocity vector we are going to update your parameter direction by adding that velocity vector with that. So velocity is being updated by derivative of the velocity minus eta learning rate of gradient vector. So this is the way. And how the momentum is going to accelerate your gradient vector here is at the peak as well as valley. At the peak it may be having a higher momentum, at the valley it may be having a lower momentum, and there are certain point it may not get any momentum also. At that time the SGD may be stuck up at that point where there is no momentum. That is the little worry of this particular method. So what is the rationale we are going to consider here is the velocity, that the terminal velocity, until we reach the terminal velocity we are going to keep on adding this momentum in our gradient vector. So what is the terminal value we expect is eta by 1 minus alpha into norm of the gradient vector. So 1 by 1 minus alpha here is the momentum hyperparameter, and if alpha is 0.9 then 1 by 1 minus alpha will be becoming 1 by 1 minus 0.9, that is nothing but 10 times. So what it indirectly means is this SGD with the momentum is having 10-fold higher speed than stochastic gradient descent. So this is the logic. That is, earlier we did only eta into gradient vector. Now what we are doing, eta by 1 minus alpha into gradient vector. Instead of having a change over the eta 1, eta 2, eta 3, here we are changing by means of the velocity. That's the change here, right? So the velocity is every time getting updated. The partial derivative of this velocity with respect to our parameter set is being considered as velocity of t, as well as the force or the acceleration is taken to be the second order derivative, that is dou squared by tau t squared of theta t. It is nothing but dou by dou t of vt. So the velocity should be a lower power here. If the power of velocity is 0, it represents the dry friction, then the force will be too strong. But when the gradient is very small but non-zero, force will become a constant. So the particle will come to a rest position before reaching the local minimum. That at this point only I told it will come to a rest position. So this has to be handled. This is the drawback of your SGD with the momentum. So to overcome that point, the next kind of optimization algorithm was being developed called SGD with Nesterov momentum. So in this SGD with the Nesterov momentum, all the stages are going to be the same. Only thing is, instead of calculating our direct gradient vector as such, what we are doing is the velocity is going to be updated by alpha times of v minus eta into the gradient of your gradient derivative of your loss function, and after that this theta is going to be updated by theta plus v, and this is the Nesterov, why we call it as a Nesterov momentum is this Nesterov momentum here decides whether to apply that update at the end or in between. That is a change over here. So what's happening here is at the early stage itself there is going to be an update. So you can see through the steps of your SGD with the Nesterov momentum. So the initial stages are the same, and until the stopping criterion is met, we are selecting a mini batch of training set with the corresponding targets. And before we calculate the gradient, we apply an interim update, early update. So the early update is helping us to avoid a settle point of the parameter direction. So that is why they are doing a interim update, and that is theta tilde theta is getting updated by theta plus initial velocity vector alpha v, and then only the gradient is being computed for the current theta delta, and based on that current theta delta the gradient is being computed, and then the velocity update is happening for the particular Nesterov momentum formulae according to the original gradient. So the gradient which is coming from your interim updated theta tilde. So accordingly the update is happening. So what's the major difference between SGD with the momentum and with the Nesterov momentum is the calculation of your update is happening in two stages. One is interim update, and finally the final update after gradient. So before gradient there is one update, and after gradient also there is one another update. So before the gradient what we are updating will be deciding are we going in the correct direction. After update will be updating your direction towards local minima. So this is the idea of your SGD with Nesterov momentum. And apart from that we are having various algorithms for adaptive regularization of your optimization in deep learning model. The fourth one what we are going to discuss is the ADAGRAD algorithm, that is adaptive gradient. So theoretical part of adaptive gradient, what is the need for this adaptive gradient, what are the situation it is handling, those and all we already discussed in the second unit. So I am just applying only the algorithm over here. So what is required for your ADAGRAD algorithm is you are going to assume the learning rate is going to be a global one. It's not going to change from mini batch to mini batch. So for every mini batch, this global learning rate eta is going to be the same. So eta naught, eta 1, eta 2, whatever the eta value we told in the SGD, here it is going to be assumed to be the constant value. And the initial theta is required to minimize your cost function. And what else we require is a small constant delta. Normally this delta value is assumed to be 10 power minus 7 for ensuring the stability of your convergence point. And what we do is initializing the gradient accumulation variable r equal to 0. So what is the idea in this particular adaptive gradient algorithm is this gradient is going to be computed for some certain amount of sample, and they are going to be aggregated together. So that is called as adaptive gradient. So the mini batch sample of training set with the sample input as well as the say target are being chosen as like our earlier algorithm, and it is going to compute the gradient for m samples with respect to your loss function as usual, and after collecting the gradient it is going to apply the squared gradient. So the squared gradient is nothing but we are taking the norm of that vector, so that is g norm of g norm, that is the squared norm of your gradient vector. So the squared norm of gradient vector is going to be accumulated in your variable r. So at the first iteration there will be a 0 value in r. At the second iteration onwards it will be having r plus the gradient norm of the previous iteration. Okay, and using that r value only, the update delta theta is going to happen on your parameter set. So the change over your parameter set theta is called as delta theta, and this delta theta is computed with the help of your global learning rate eta as well as your small constant delta. So what was the value we chosen for small constant delta? It is 10 power minus 7, right? So minus eta divided by delta plus square root of r is going to be multiplied with your gradient, and that is going to be called as your change over your parameter direction, and that direction is going to be added with your or updated with your current parameter direction. So this is the way the ADA gradient algorithm is calculating your optimization value for achieving the lowest cost function. The fifth technique is called as RMS prop algorithm, and this RMS prop is slightly deviating from your ADA grad by having another parameter called a decay rate, but eventually all the other stages are same. Only thing is it is adding an extra parameter called a decay rate rho. Okay, so initially the accumulation variable r is set to be a 0 until the stopping criterion is met. What do? We take a mini batch, we are computing the gradient here, and after computing the gradient we are going for accumulating the squared gradient by using your accumulated variable r as well as your rho, that is the decay rate. So r is getting a new value for its gradient by taking the ratio of rho times of old value of r plus 1 minus rho times of current norm of the gradient. Okay, and finally the delta theta, that is the change over the parameter direction, is as usual decided by minus eta by square root of delta plus r with by making a inner product of your gradient vector. And finally the final update is happening as theta plus delta theta. And here how the rho plays a role in this particular RMS prop is this rho value control the length scale of the moving average. So what we mean to say is the accumulated squared gradient, how far are we going to accumulate, that is being controlled by how far means how many stages of gradient are we going to keep, that is decided by the rho value. And this RMS prop further improvised by the next algorithm called RMS prop with Nestor momentum. Here the interim update is initially calculated, all the other stages are the same, I am not writing anything. So the interim update is happening as usual, as like your ADA grad theta delta with theta plus alpha v, and then the gradient is being computed with that theta delta, and the accumulated gradient is computed as like your RMS prop, and then the velocity update is happening v as the alpha v minus eta by square root of r in the inner product with g. And what you can observe here is it is the combination of Nestor momentum as well as the RMS prop. It has both the inherent qualities of those optimization algorithm together, hence the name is called as RMS prop with Nestor momentum. And the last algorithm what we are going to discuss is the ADAM algorithm, which is otherwise known as adaptive moment. ADA grad is adaptive gradient, ADAM is adaptive moment. And here what is needed is we need many more initial values, that is one such value is step size eta, it is 0.001. The minimum value we expect is 0.001. followed by an exponential decay rate for moment estimates called rho 1, rho 2 in the range of 0 to 1. It can be either 0, but it cannot be equal to 0 or equal to 1 or greater than 1. And the rho 1, rho 2 normally is assumed to be 0.9 as well as 0.999. And the additional small constant parameter, as like your ADA grad, it is also having a delta parameter with a value of 10 power minus 8 for making the stability in convergence. So the initial parameter theta is being taken, and the first and second moment variables, as we are considering rho 1 as well as rho 2, we are using two moment variable for accumulating the gradient for the first order as well as second order. So they are initialized to be s equal to 0 as well as r equal to 0. So r is maintaining the first order gradient, s is going to maintain the second order gradient, and we initialize the time step of our algorithm with the value 0, and until the stopping criterion of your cost function is obtained, we are repeating the algorithm by initially taking a mini batch training set with m different sample along with their target. Okay, and then we are computing initially the gradient of the loss function with respect to your parameter set theta, and what we do is we are updating our biased first moment estimate by using our factor as well as your rho 1, whereas the second moment estimate is being updated with the help of your rho 2 as well as the initialized moment variable r. So first moment variable is, first order moment variable is s, second order moment variable is r, and finally after update it is going to be uploaded over our parameter direction. Before we going to upload into the parameter direction, we are correcting the bias in the first moment with a factor of our 1 minus rho with respect to the time ratio. As the time increases, the 1 minus rho 1 to the power t is going to reduce that value, so automatically s cap will be keep on increasing in a very slow rate. Similarly for your r cap also, after finding the s cap as well as r cap, when you apply the formula as like our RMS prop algorithm, here also you are having the same update rule, and finally what we get is theta plus delta theta, where the delta theta is nothing but minus eta s cap divided by square root of r cap plus delta. So these are the various algorithm for doing our optimization over the deep learning model. In the next class we will see how are we going to make use of the other two methods rather than this gradient based method. We are going to see conjugate gradient as well as the last one what we are going to see is the Newton method. Okay, fine.